This is about the intermediate value theorem, and it's a very nice little theorem. It's very logical. So we'll just read through it and we'll figure this out. So suppose f is continuous on the closed interval a, b. So we have some function f here. This is our f of x. And we're going from a to b, and it's closed. So we have this nice closed interval like that. Let n be any number between f of a and f of b. So this would be right here. That would be our f of a. And this point would be our f of b. So we have f of b and we have f of a. And so our n is some number that is in between these two, where our f of a and f of b don't equal each other. Makes sense. Then there must exist a number c in a and b, so some c within here, such that f of c equals n, which makes sense. If we're continuous, then if I'm going to graph from a to b, I cannot pick up my pencil because it is continuous, which means that all the numbers between f of a and f of b have to exist for y values, which means there must be some a through b value, some value c that gives you n. So basically we have like some n here. So if you trace that back, there has to be some c that would give us f of c equals n. It's just a logical thing that if you can't pick up your pencil, then all the numbers have to exist. So let me show you an example of this, and hopefully you'll see why this intermediate value theorem works. And it just means that there's an intermediate value between the f of a and the f of b. Okay, so we're going to look at Desmos. I've already got the graph here. You can find this on my website as well. So g of x is equal to this polynomial. Show that there is a number c such that g of c is equal to 1. So we're just trying to find that there is some y value equal to 1 and that there is some x value that will give it to us. So we already know that this is a polynomial. So is g continuous? Yes, because it is a polynomial. All polynomials are continuous. Okay, so let's look at the graph. So I've already played with the polynomial, and I just picked a nice little interval that works for us. So if you look at this, this is your y values that are in between there. The y values are going to go from -2 for an x of -2 to an x of -1.4 in there. And you can see these are all the y values that exist. So since our polynomial is continuous, then the lowest y value from -2 to -1.4 is -10. And the highest y value from -2 to -1.4 is 4.07. So that means all those y values from -2 to -4.7 have to exist for our functions, which means there has to be x values that give them. And these x values are between -2 and -1.4. So that's what we're talking about here with an intermediate value, that there has to be some value in there. So if our y value is between these two, there has to be some x value that will give it to us. So that's all we're doing, is saying that there's some intermediate value between these 2 points. So if you lock a y value and another y value and it's continuous, guess what? All the y values between them exist. So if you have a y value of -20 and a y value of 100 and it's continuous, there are y values between -20 and 100 within there. So what we need to do now is find an interval AB where g of c is equal to 1, and that's what I've done with this picture. So you could see that right now there is a 1 there. Right here is 1. All right. Now we're not going to find the x value that gets there. I would have to sit here and play with it a lot to try and find it. We don't have to find it. We're just saying that there is a 1 for a y value. So if I take this x value, my a, and make that my f of a, and I make this my b, and this my f of b, then by doing that and saying it's continuous, and I'm using the intermediate value theorem to say that there is a 1. So it looks like this. So I now have looked at my graph, right? We've looked at the graph, and I go, okay, well, 1, my y value would be between -10 and 4. So if I pick -2 for my a, and I pick -1.4 for my b, that will give me the y values that will give me what I need for the intermediate value. So you first start by stating that it's a polynomial, and then you plug in those two values. So we're going to plug in -2 and we're going to plug in -1.4. And you're going to be using either Desmos, and so we're going to get negative 10 and 4.07. Or you could take the graphing calculator, plug it in there, hit zoom 6 to get an idea of what the graph looks like. And so you can see there's a 1. And so right in here is a 1. So it's between negative 2 and I could even say negative 1. But I've already picked the two numbers. So my x between negative 2 and negative 1 would give me that 1 that I need for the y value. So if I go trace negative 2 and hit enter, it tells me my y value. Trace negative 1.4, it tells me my y value, 4.07. And now we say that g of c is between that. So you can now say, well, g of negative 2 is equal to negative 10. And our g of c is greater than that, which is less than our g of negative 1.4. And our c is between negative 2 and negative 1.4. Therefore, there must be a g of c equal to 1 by the intermediate value theorem. So all you're doing is finding two y values, one that's smaller than the one you want. So our y here is 1. That's our goal. And so if you find a y value that's less than 1 and a y value that's more than 1, and the function is continuous on that interval, right? This is continuous because it is a polynomial, then the intermediate values theorem states that there has to be something in between. It has to be an intermediate value. So you just need those two conditions. It needs to be continuous on a closed interval, right? And that n, the value you're looking for, has to be between these two. So if you say that it's continuous, you write the interval that it's between, you just show that that value exists. So we can also use this for roots. So right now we're going to show that there is a root, some p of x equal to 0 for this equation. So let's first make our function. Let me put this in blue this time. So p of x is equal to 4x cubed minus 6x squared plus 3x minus 2. So what we're trying to do is show that there's basically a solution to this equation, right? That there's something that will help it equal 0. And that solution is between 1 and 2. So if we plug in p of 1 and we plug in p of 2, in order to get a 0, that means we need a negative and a positive. So think about it. If we want to show that our polynomial is equal to 0, that would mean that we are on the x-axis. And so when our function comes through here, it just needs a p of x, so a p of b, why am I putting a parentheses there, a p of b equal to a positive, and a p of a equal to a negative. And it doesn't matter the order of these two, it just has to be one negative, one positive, because to go from a negative to a positive, you have to cross through 0. So that would show that there is a p of c of 0. So it's very quick. We take our polynomial, plug in our calculator, plug in 1, plug in 2, one's negative, one's positive. Guess what? We've got a solution between 1 and 2. So we plug that in our calculator, 4x cubed minus 6x squared plus 3x minus 2. Hit zoom 6 for a standard graph, but we're not going to even do that. What we're going to do is go back to our window, and we're going to plug in 1 and 2, because that is our interval. And so this also gives us a picture of whether it crosses, and there it is. You see there is, it's crossing right there. And so now when we go trace 1, it says that it is negative 1. And we do trace 2, and it says it is 12. So you can see that we're getting a negative 1 and a positive 12 here. So that means that p of 1 is less than, oops, that's right what it says, p of 1 equals negative 1 is less than p of c equals 0, which is less than p of 2 equals 12. P of x is continuous, so we're going to write that. Oops, forgot the p of x. P of x is a polynomial. So continuous. And this, and we know that our c is between 1 and 2. Therefore, there must be a root, or p of x equal to 0 between 1 and 2 by the intermediate value theorem. So I hope you get the idea of what we're doing here. It's basically you find a number less than what you want and a number more than what you're looking for, and if you can do that with a continuous function, you can then use the intermediate value theorem. So it works with anything, even rationals. If you had some rational which has an absolute value over here, that doesn't matter, because if you're looking for this value, you just have to lock it in here. So if you found a -2, it's negative now, but just ignore that line, and a 10, that means all the values along here have to exist because it is continuous on that interval. It's not continuous after it. So like our asymptote would be at 15. It doesn't matter. It's continuous here. So this value has to exist, and you could use the intermediate value theorem to show that it does. All right, thank you.